Thank you. Thank you very much for the nice presentation, nice introduction. Okay, thank you very much, everyone, for being here for this presentation on secure firmware updates on safety critical systems, which includes, of course, items you're going to send to space. And we're talking today about secure firmware updates and secure boot and a few things related to functional safety as well. And what has been our experience so far working on airborne secure bootloader especially. So I work for this company. It's called WolfSSL. You probably have seen the stand there in the main area. And our focus is obviously on cybersecurity. We're not directly working only on the aerospace vertical. We are quite an horizontal company, actually, working together with multiple companies and in different industries from, of course, aerospace, but also biomedical, automotive, industrial automation, IoT, all kinds of things. So we're very popular in the embedded world because of a few characteristics we will explore probably in this presentation. The company is US-based. It has more than 2,000 OEM customers. And everything we do is dual licensed, so it's open source under GPL license. And we also offer proprietary licenses for commercial products that cannot comply with the copyleft. And but of course, this means that all the source code for all the things I'm going to talk about is available on GitHub. And we do also offer professional support services from our engineering team. Our main areas of focus are actually three. We have securing data address, so whatever is related to cryptography, authentication, as we will see, encryption. Securing data in transit, that means mostly applying those standards that target data in transit, specifically SSL, or what's called today TLS, but also other protocols like SSH. And we do that, of course, in a transport agnostic way, so we can work with any kind of media. So from, of course, TCP/IP, which is the preferred option from the standards, but this means that we can also run on custom protocols such as, I don't know, Bluetooth or serial lines. Some customers like TLS over CAN bus, for instance. And the third area, that's where we focus more today, it's firmware updates. So we secure our firmware transfer using those technologies in the second pillar. But of course, we also have a number of countermeasures to prevent malicious firmware flashing or injection of malware or tampering with the devices if they are physically reached and you didn't send them to space yet. This is a bit an overview of our product. I'm not going to stay a long time on this slide, but just to let you know that our flagship product has the same name as the company. It's called WolfSSL. That's a TLS SSL implementation that scales down to the smallest microcontrollers up to the largest system you can think. And then down up until WolfBoot, that's the one highlighted in green. That's our secure bootloader, and that's what we're talking mostly about today. What is secure boot? Secure boot traditionally means preventing a third party to run unauthorized software on your target, on your device, on your embedded system. How do we prevent this? We prevent this using traditional cryptography. Traditional and less traditional, we will see. So a cryptographic signature is attached to the image that you want to transfer. In that case, it's going to be your firmware probably for your device. And that signature is obtained through a public key algorithm. So using a private key, actually, you can sign any payload. In this case, it's going to be your firmware itself. And then the secure bootloader main task is to refuse to boot if the signature for authenticating the firmware itself doesn't check, so it can be verified. which means that any modification made to the original trusted source will be automatically recognized by the bootloader, and the update will be discarded. One thing that works in cybersecurity on safety critical system has to deal with is that security does not imply safety, but also the other way around. Software safety does not imply security by default. That's probably a very well-known statement at this point for all of you. But the software that's considered secure for IT might be not sufficiently safe for a safety-critical environment. And specifically in this talk, we stress about DO-178C, because DO-178C is a very well-established and well-formulated, in our opinion, safety regulation specifically for airborne software. A few things that are mandated by DO-178C is that there should be no dynamic memory allocation allowed, and we want everything to be predictable at compile time. So for all those of you that are fan of this new safe programming languages, C can be safe if you don't use part of it. So if you restrict yourself and never call a malloc, for instance, you don't have to worry too much about memory allocations, or at all. And that's actually, there is a way to write safe C. And that's not the case for application, maybe, but for system components, that's definitely what we want to do. And the software needs to be written in a way that it must follow guidelines and standards and can be traceable backwards to its own specification. We will see that DO-178 requires a mapping between what the specifications are and what the software looks like. And this mapping needs to be also validated through the use of specific test procedures at different levels. So you have higher level of requirements that need to match your functional tests. You have low-level requirements that need to match your first batch of unit tests, and so on. And of course, this process is bidirectional, right? So every single line of code needs to be, let's say, a reason to exist, because that's written in the specification that the software needs to do that. So, and this is done line by line. And this is, the traceability is one of the main requirements of DO-178C certification. A certification lab will perform code review on your code, and then we maintain and fix the code. We take care of the requirements coverage and the structural coverage analysis, and we have let's say, interaction with the lab to ensure that your product eventually will respect the DO-178C requirements. So that process has been done for Wolfboot as well this year. So before that, we already had DO-178C certified crypto library, which is the core of Wolfboot itself. And we are applying this to secure bootloaders that are on board of avionics systems, so that are actually airborne. So, is there a standard, since we do everything according to standards, is there a standard for secure firmware updates? Well, when we started back in 2018, there wasn't. But there was a team within the IETF that was working on it, the CYSAT group, and they were working on a draft for that. And we decided to just adopt that draft since the beginning, which eventually, in 2021, has been standardized into RFC 1919, which is an advisory RFC that specifies how secure bootloader should be written. And the requirements are that the bootloader should be agnostic on how firmware images are distributed. So this is up to the application. The application needs to decide how the firmware goes from your infrastructure, your cloud server, whatever, to your device. So that's not responsibility of the bootloader itself. what the bootloader needs to do is verify the authenticity through well-established cryptographic algorithm, especially asymmetric cryptography, which is a public key mechanism that we use for verifying the firmware itself. That's how WolfBoot was born. It was written in C for bare metal use, and of course, there's no OS when you turn on your device. We're responsible to verify that the OS is actually being signed if you're using an OS. It has a very small footprint. We range between 8, 9 kilobytes till 32 kilobytes of microcontrollers, so it can fit really, really small devices. There's a simple partitioning scheme. By default, that can be extended, of course, according to the use case. And we have a good abstraction of the hardware, so it is easy to port from one target to the next one. The bootloader doesn't deal with the transport of the image, but it does deal with the swapping of the images if required within the target. And we also distribute key tools that can be compiled for Windows, Linux, and Mac, that allow you to manage your keys and use them to sign specific firmware that have been assigned to a specific version, etc. WolfBoot relies on WolfCrypt, which is our crypto engine, and it's FIPS 140-2, almost -3 certified, a matter of days, maybe weeks. We have that, as I mentioned earlier, certified already for airborne systems, and we are using a few, we have an option of using different asymmetric algorithms, including ECC, RSA, Edward curves, and new post-quantum cryptography that I will mention shortly. It has a number of features that are very important for secure boot in general. So it handles the update in a power fail-safe manner. So you can turn off the power to your device in the worst possible moment while the bootloader is swapping your two partitions, and the operation will be resumed from that exit point and the next boot. So this ensures that you don't send to space $1 million brick. And you can also do encrypted updates, delta updates, a number of features that you will not find in other bootloader on the market. So we support several architectures, and we have new features that we introduced this year. You can see all the architectures we support. We started on the Cortex-M because of market reasons. A lot of companies want to use secure boot on small microcontrollers. We migrated to Cortex-R and then to Cortex-A even, so we are capable of replacing more complex bootloaders with a secure bootloader. And we recently ported to Intel x86-64, not just as one of the steps in your bootloader chain, but as a BIOS replacement. And this is an operation we've done in cooperation with Intel, and we have used what they call the firmware support package that allow you to replace the first stages of boot with your own BIOS, basically. So that's what WolfBoot is on those machines, especially our first port was on the Tiger Lake. It replaces the BIOS of your system, so it can connect to the Intel boot guard mechanism at the very early stages of the system. Other important features we added this year, PKCS11 crypto engine, hidden in your trust zone M within your Cortex-M 23, 33, 35 devices, where you have a trust zone M, so you have a domain separation. So we can the bootloader runs in secure mode and will stage your application in non-secure mode, but will also offer an interface to access those any generic purpose cryptography that you might need through, let's say, a trusted execution environment which runs in the secure domain of those microcontrollers. And last but not least, we added two new cryptography algorithms, namely LMS and XMSS, because those are the PQC algorithms that Sven was mentioning in the previous talk. So those algorithms that are meant to replace your pre-quantum algorithms that we've been using so far. And this is especially important for customers who have products that have a very long lifetime. For instance, they need to be in the space for the next 20 years. And it's better that they have some algorithms in place that cannot be broken by a quantum computer that will be probably available by that time. So that's why LMS and XMSS, even if NIST is still in a draft of finalizing the algorithms to be selected, it seems obvious to us, looking at the market, that most chip manufacturers are, and HSM, and are looking at LMS and XMSS for the specific purpose of signature verification. We, of course, have other post-quantum algorithms implemented that are less relevant for secure boot, but we use in a hybrid cipher suits, for instance, for TLS. But we won't talk about this today. Oh, yeah. How does WolfBoot work in terms of key management? Key pair is generated once on your machine. Your private key is the basically the only thing that cannot be disclosed, because it's never shared anywhere. So it's just used for signing your firmware, but it's not distributed on your devices. Its counterpart is a public key that is basically used to verify that signature. And the sign tool attaches this manifest header to the firmware update that we are sending. And this manifest header contains the signature, contains also SHA-digest, for instance, to verify the integrity. And the only requirement on your device for WolfBoot is to have a trust anchor to embed the public key that's used to verify the signature. What's a trust anchor? This is also defined by IETF, and it's just basically, it's a public key container. So it doesn't need to be protected from reading because it's a public key. So by definition, that implies no risk. The only thing is that it cannot be modified by an attacker. That can be done in different ways through read protection or storing the public key in a key store or in a vault or something. There's two possible strategies on how to handle the updates. One is the AB approach, so the two partitions are equivalent, and that's mostly for microprocessor devices where the two partitions are equivalent, and then the bootloader will decide through an election which one to boot, and they don't have any requirement in terms of physical memory. On microcontrollers, by the way, you need a physical address from starting the firmware there, so you need a boot update approach, so the two partitions are not any longer equivalent, and you will have to swap the content of the two when you validated the update as a valid one. And of course, this means that on microcontrollers you need an extra partition as a swap partition that's as big as one sector on the physical memory in order to be able to swap. We do have a few fail-safe countermeasures. I was already defining the $1 million brick avoidance mechanism. So the power can be interrupted anywhere, and microcontroller can be reset at any time, but we guarantee that there is always one image that will be capable of booting the device. So we have a mechanism to confirm the update, or in case rollback to the previous version. In case the update is valid from the signature point of view, but it doesn't boot properly or doesn't get to a barrier point when you can confirm that the update was successful. One thing we worked a lot on is side channel and glitch attack mitigation. There are existing mechanisms capable to skipping single instructions in the device, and of course, for verifying a signature, if you skip the right instructions, it means that you can basically override the bootloader. No other bootloader has that, but we have specific countermeasures for this that you can check because our code is open source, of course. And that basically, it's a bunch of assembly that make all these operations redundant and put some canary values. There's a few function pointers mechanism to do this. So this has been extensively worked on and verified by third parties that specialize on this kind of attack. And we can also integrate with third-party signing services, and it's especially important for post-quantum signature because post-quantum private keys cannot be exported and needs to be used exactly where they have been generated. So usually you want to use a third-party HSM to deal with this post-quantum private keys. I think I'm running out of time, but this is mostly how it works in microcontrollers. You have the two partitions we're talking about, and swapping back and forth is an operation that the bootloader takes care of. On our most complex target, which is an Intel 11th generation Intel Core i7 CPU, the boot strategy is much more complicated. I won't have time to tell you all the details about it, but I'll invite you to read all our white papers and blog posts that we have published about this in cooperation with Intel, guiding us through this mechanism and how it works from there to the boot procedure and actually multi-boot Linux cell for whatever operating system you want to start from there. So the 0178C integration is at a good point. At this point, we have almost finished the validation. We have stripped down all our code. We trimmed the code, and we have we're ready to ship for any kind of safety critical system. And these are a few of the reasons why you should replace your existing bootloader with WolfBoot, and especially thanks to the quality of our cryptography and that we can apply, and the fact that we are ready to any kind of safety regulation or security certifications, since we are in the FIPS 140-3 validated cryptography there. So this concludes my presentation for today, and I welcome any questions.
Thank you very much for another really interesting presentation. That was great. I ask you again, if you have questions and you'd like to submit them online, feel free to use the tag that should be on the screen soon, hopefully. And if not, are there questions in person? Who would like to start us off?
One there.
One right at the back. Line. Nice. Where's the question?
I will try to explain. How do you manage, because I feel there's a vulnerability about the redundancy of two bootloaders, because we have to switch the starting address, the booting address. How do you manage to process this? I think it's a vulnerability of the system.
So, are you talking about microprocessor or microcontroller?
Your system, you have two redundant bootloader.
Oh, okay, okay. So
you have to switch to process the how will you spell it? The break avoidance, the tune miner.
Oh, all right, okay, okay. So basically, what happens there? Let's say that you have this microcontroller and you have the two partitions, right? One is the boot partition that contains, let's say, your factory images version 1, and you just sent a version 2 over the air to the second partition. And there is a swap partition at the end, which is as big as a single sector. If I start swapping the partitions one sector at a time, I will always have two copies of the same sector, right? One is in the original partition where the copy is originating, and one is in the swap partition. And every time I finish the copy of a single sector, I mark with a flag that uses some properties of the flash memory, so it adds zeros, bits to it, so that it's basically an atomic operation. And if it doesn't complete, if the shutdown is exactly there, it doesn't matter because you still have two copies there. But when the copy is over, we update the flag, etc. So in any time you interrupt a copy, a bootloader will see which was the last sector that was copied successfully, and will recover the next sector depending on the value of the flags from the origin partition or from the swap partition, and then resume the operation exactly from there in order to conclude the the actual swapping of the two partitions. So it's a state that's updated using flags and using operations that can be interrupted before the flag is updated.
Are you happy with that response? Cool. Can we? Okay. Do you want to ask one more question? And then no. Okay. Cool.
We can take this offline if you want.
Yeah, might be a good idea. You've got lots of interest. So another question here.
Thank you. The question is, you mentioned delta updates, because, for example, for our satellite, we don't have too much bandwidth. I would like to know, how do you deal with that, and more details?
That's perfect. That's a great question. Thank you. So delta updates are not designed for having a smaller update partition, but exactly for the use case you're saying. So having as quick as possible update, and that's if you have a LEO, of course, you have a short time to transfer there, and that's a perfect use case. We're using a Bentley-McElroy algorithm to have a binary difference between the previous version and the next one. Of course, you have to keep track on which version you think is on the target at this moment, but the delta is usually much smaller than the entire partition. And if not, you can do that multiple steps and upgrade version 1, 2, then 3, then 4, etc. But it's just this delta is signed, so it will be verified the moment it gets to the target, and then it will be applied to the update resulting in the update partition image that will be verified again, because of course it's two different signatures. One is for the delta and one is for the actual image that will rebuild the image as if you transferred it in total. No problem. Thank you.
So I'm just checking online. Remember to add your questions on. We've only got a couple more minutes for questions. So are there any other questions in the room? I can see one over there. Cool. I'm coming over.
You briefly touched this bootloader replacement, which is not power fail safe. How do you handle that?
Okay, so that's an excellent question as well. So it's we run temporarily from RAM, and we can swap ourselves. Basically, you get an update that's signed exactly as an application, but it has a flag that says this is a bootloader. So at that point, I jump to RAM, and I just replace the image of the bootloader itself. But we consider this still an emergency procedure because exactly the reason you said it's not power fail safe. Unless you're using a microcontroller that has a dual bank, in that case it's power fail safe as well, but not all of them support that.
Thank you very much for another really brilliant presentation. Yeah, thank you, Daniele.